Welcome to a lesson with Powell. We're going to talk about a few formulas that help us know how far off we are when we're doing the trapezoid rule or the midpoint rule or Simpson's rule to approximate an integral. And we're not only going to see what those formulas are, but where they come from as well. I have a little web page with this address that actually runs through some calculations here, and that's where we're going to go. All right. So looking at this, and I am going to make that a little bit more like that. Okay. So in the code below, we run a computation that figures out a formula for the error bound for the trapezoid rule. So let's first start with the trapezoid rule. And I'm going to kind of explain kind of where this rule comes from and what it is. First, I'm just going to push this button and let's see what it outputs. Wow, what does all that mean? And then you see this thing right here. Okay, let's come down here and look at something. This right here. This is actually the error formula for the trapezoid rule. And somehow it's coming from this thing that came out of a computation, which I was running up here. And right here is a description of how that computation went and what was going into it. But in the end, we end up getting this. This is our error. What in the world do these things mean? Well, let's take a look at this. And okay, so this m right here, it just simply means a bound for second derivative of f when we're integrating on an interval from a to b, f of x dx. Okay, so this is what we're integrating, and we take f double prime. What's the biggest that f double prime, the second derivative, can be on the interval from a to b? So, and pick a number m that's bigger. Well, at smallest is the biggest that this can be, but basically it bounds this above. So, for instance, if f double prime was e to the x, and e to the x is an increasing function. So if f of x is e to the x, and then f double prime will also be e to the x. And let's think about this. If we're on the interval from 0 to 1, what's the biggest e to the x can be on 0 to 1? Well, if we look at this, e to the x is an increasing function, so you look at the right-hand points, the biggest it could be is like e to the 1. So m in that case would be e to the 1. So we can figure out what m is. It's just upper bound for the absolute value of f double prime. B minus a, we can get that readily just from thinking of the endpoints. In this case, if we had 0 to 1, it'd just be 1 minus 0. This 12n squared, what does that n mean? N is just the number of subintervals that we're using. So we're looking at this integral and we're approximating it with the trapezoid rule. So we have an interval from a to b, and we've split this up into some subintervals. So let's suppose n of them, and then we have some function going on here. So the trapezoid rule, remember, just calculates areas of trapezoids. Take these two endpoints, you draw a line here, and you're just kind of doing all these trapezoids as we go along. So what's the error? How far off is that? And this gives us an inequality for that. And n is the number of the number of subintervals that we're using. Okay, so that's what we're after, and that's what we're looking for in that calculation. All right. So sometimes it's nice to have an idea for why something's true and where it comes from, and what in the world does all this mean right here. It kind of looks like, in some sense, it kind of looks like something would come from a Taylor series. If you let's intuitively see why that would come from a Taylor series or how. You can almost think of, see this 12? This 12 is kind of like, it's 3 factorial times 2. So there's an extra 2 sitting out here, and there's an m. So let's just kind of set those off to the side. But let's look at everything else that's happening. Then there's so 3 factorial times 2 is right here. So there's like a 3 factorial. And then if you think of this, I'm going to add in an extra n in the denominator. So I'm going to times top and bottom by n for a minute. So the reason why I'm doing that, because this is going to look like b minus a over n cubed. All right, so I'm just going to call that guy in there. I'm just going to call that h. So this right here is going to look like h cubed. So it's kind of like h cubed over 3 factorial. And then you're multiplying by n. It turns out that this part actually is a bound for the error on one subinterval. Each subinterval has this as a length, b minus a over n. So I'm letting h be equal to the length of one subinterval. So one subinterval is going to have this length because we have b minus a, which is the total length, and divide that into n pieces. How big is each piece? Is b minus a over n. So this is the size of each piece, which I'll just label as h. So on one of those, this right here is actually an upper bound for the error on one subinterval. Then guess what you do? You just multiply all that by n for n subintervals, and therefore we get the error. So now look at this part right here. See, it's h cubed over 3 factorial. That looks like it comes from some kind of Taylor series, right? And then somehow we get this coming in as well. In fact, kind of what we're missing here is we're missing something to do with like a derivative and plugging in, hopefully like a third derivative, plug something in the center, and hopefully that's represented. This represents something like that. But what would be, since this represents the error, though, we'd need like a Taylor series that represents the error. And actually, that's exactly what the computation does. So let's take a look at that for a minute and see what's going on. All right. With that in mind, maybe look up here, kind of building up into it. In fact, kind of what we're doing is we look at actually the Taylor series of the antiderivative of f of x. Let's just start there. So the antiderivative of f of x. Why in the world would you want the antiderivative of f of x? Because if you think about one subinterval of length h and you start at a, so this is like the first subinterval, like you're at a, and so this first subinterval, like if we split this up, like we're going from A to B, and this first guy is going to be a length of h, right? So we're going to have a length of h first of all. So this integral right here, let's see, this represents the actual integral of f of x, but just on the first subinterval. So this is the actual integral. We're gonna think about this actual integral in terms of a Taylor series. And in terms of the Taylor series of actually the antiderivative of f, which is capital F. Now, what is this? This is actually equal to this, right? If you take an antiderivative of little f, you get big F, and you plug in a plus h, and then you plug in a and you subtract. So that's what that's equal to. Now, if we had a Taylor series for f, then what we do is we plug a plus h into that Taylor series, then we plug a into that Taylor series, and we subtract. And what we end up getting is a Taylor series for the integral. So the integral, we get a series that actually equals this integral, and this series came from a series for the antiderivative of f itself. So, and in the code above, the symbol f int, or kind of that, is like kind of like the code name for that Taylor series that represents the actual integral. So then so that's great. So we get this, so we get a Taylor series or f int, and it's centered at, this Taylor series is centered at a, but then notice, so, but then we're sticking an a plus h into there. Now, when you stick a plus h into a Taylor series that's centered at a, look what happens. It's like x minus a, right? So replace x with a plus h and subtract a. Everything is actually in powers of h now. So it's really like a Maclaurin series with variable h, where centered at h is equal to 0 if you want. So you can actually think of this as a Taylor series in h, a variable h, which is kind of what we were seeing before, um, where it's centered actually at an h value of 0. And so that's kind of what we'll be looking at when we look at all of these series as we go along. So the first series that we need is one that represents the integral. Now, what else do we need? We just need a series that represents the trapezoid rule on that first subinterval, just with an interval, with one interval. And we subtract those, and that should be the error. And if they're both in terms of powers of h, then this is really nice, because then we get the Taylor series for the error all in terms of h. Okay, so let's take a look at that. All right, so how do we end up getting the Taylor series for the for the trapezoid rule? Well, we just look at this right here. So this is how you compute the trapezoid rule on one subinterval. You take the average of f of a and f of a plus h, so like on the two ends. So think about this. You have one subinterval of a plus h, and on the two ends you find the height there and the height there. Find the average of those two guys, and then multiply by the width, and that's the area of the trapezoid in there. So that's all we do. So we're just going to take this, and so we need a Taylor series for this expression. Now, the way we do this is actually we develop a Taylor series for f instead of f prime, or for big F. So here for the integral, we use a Taylor series for capital F. Now, for this one, we're going to use a Taylor series for lowercase f, which will be a little bit different than this one with the coefficients. Now, when we do this, okay, with f, and part of that has to do because we're taking because go from capital F to lowercase f, we've taken a derivative. Coefficients will change. But here, just think about the formula for the Taylor series for just f itself, but we're dealing with, and it's centered at a, but then when we're plugging in f of a plus h, that part will just have powers of h. When we plug in a, we're just going to think of that as a constant. In fact, in the code above, we just use the symbol f to represent f of a itself, and then we use the symbol fxx to actually represent f prime of a, or sorry, f double prime of a. If I have a fxx, I meant to write an fx. If I just have an fx, that's an f prime of a. And that's kind of symbolically what these things mean. And in particular, this f double prime is the same thing as capital F triple prime. So those, but we're going to express everything in terms of the in relation to f. Even the Taylor series that came from capital F, we'll write like its third derivative, we'll write as fxx, because it's f is already the derivative of capital F. So we're going to do that so that we can kind of correlate coefficients and compare things in a nice way. So we write one power series, one Taylor series. We write a Taylor series for this by plugging this into a Taylor series of that, doing this computation, multiplying by h into the series, and this is a constant, adding it in. We do that, and we get a Taylor series here. We take the subtraction of the two, and we get a Taylor series for the error. Okay, now let's take a look at this computation for a minute and see what happens and what's going on. So we have some variables, like I said, we just kind of list these out as, and we know kind of what they mean. I kind of did this kind of compactly, but really this is what we're getting. So f int of h, Basically, we take the Taylor series for capital F, and we subtract off capital F of A, which gets rid of the first term. So then we start the second term, and F is like capital F prime of A, and then we just keep going and then we have H. Now we're in terms of powers of H, just like as we were describing, H squared, and so forth. This is the second derivative of capital F, third derivative of capital F. Here we have our 1 over our factorials, just as we would expect. That's what F int is, because really we just subtract off F of A, and which we're just taking away the first term. And then this is simply the integral written as a Taylor series in H. All right, now what about the the Taylor series for F itself? Very well, it's just as you would expect. It's just this is the first guy, F of A, F prime of A times H. It's nothing new. It's just that. So then what we're doing is we're just taking, this is the trapezoid part right here. We take this is F of A plus the Taylor series of F with H plugged in, so it's just H away from A. So we this is A plus H, basically, F of A plus H, and this is F of A. Add them together, divide by 2, multiply by H. That's the result of the trapezoid rule. Subtract off the Taylor series in H4 that represents the integral. That gives you the error Taylor series. Okay, now the rest of this just kind of figures out what the different coefficients are of this error series. And if we go through and look at that, see a coefficient of H. So basically there's no constant. There's no first degree term, no second degree. The lowest one is a third degree term, and it's 1 over 12 times fxx. And then if you let H be equal to B minus A over N, and you plug it in, then multiply it by an additional N, you end up getting the formula that we want, which actually represents the error bound. The only problem is this fxx is supposed to be representing the second derivative of f with a plugged in, the beginning of the subinterval. But how in the world does this correspond? Now here comes the question. It's really nice because this looks exactly like the error formula, but a little different. In the error formula, we have a capital M, an upper bound for the second derivative. Here we just have f double prime of A. Well, I have right here another video which can be watched if you're interested at this particular website, you can click here. This is the derivation of Taylor's remainder by nested integrals, and here I give a little description as well to kind of explain. But the gist of the idea is that it's okay to replace. So we go to the lowest power term in the Taylor series itself, and then you replace the part that represents, okay, so you replace the coefficient by the biggest that coefficient could be on if we had kind of changed our parameters around in the whole interval. That's kind of a very loose, vague statement. You could make it precise, but if you do that, it actually bounds the whole series. So really, if you get a bound for there and then you put it into the first term, you're really bounding the whole series from that point on. And you can get a sense for how that would work in as you derive Taylor's remainder or even Taylor's formula itself by kind of a nested integration, how you get from one term to the next. And the essence, we always have an integral that you're working with. And that integral itself, you can if you can bound the integrand, and bounding the integrand is the same thing as like putting a constant in there. And the way you get your specific term is by like is by actually pretending you have a constant in there plus more stuff. And that constant itself, you end up getting a term. But what if instead of just having that constant plus stuff, you just had something and bounded all of it right there? It'd be a constant. You have the same basic calculation to get the error. So that's kind of a rough statement, but it works. And so in the Taylor series itself for the error, you just look at the lowest non-zero occurring term, and you just replace, this guy that can vary by an upper bound of it, and you actually have the error, or a bound for the error. So a bound for the trapezoid rule would be this. In a similar way, I run through a same type of computation that does the midpoint rule, and you end up getting this. In fact, you can execute this code and you see it right here is the formula for the upper bound for the midpoint rule. See the midpoint rule in action. Really, the only thing different here is just this EM. So we're actually using what we had up. Let's see. We're using the F and int from before. So you have to run the code cell before, and then you can run this one. Don't try to run this one before the other one, because you actually need the F int that was defined in the other one. So here you have this calculation for the midpoint. Now, this is really just the midpoint on one subinterval. It's really easy. You just take the function itself, f, and you plug in the middle of the interval, and then you multiply by the length of the interval. That's it. Okay, so and this actually gives you the Taylor series for the error in terms of h, and then we just figure out what the lowest occurring non-zero term is, and we see it's this. And from there, we can, or it's actually this, but then times h cubed, but then you plug in this and multiply by n. So you get that, and then you just replace fxx with a bound, upper bound, and that's where we get this formula right here. So essential was getting that constant out, and it was a coefficient of x cubed, which would be third derivative of capital F, or second derivative of little f, but then of course you're combining series and adding things up a little bit. So Simpson's rule. We can do the same thing for Simpson's rule. So let's. Okay, and when we do Simpson's rule, look, it takes us all the way down to here. It's a pretty good approximation. We're starting, so the further we get into the Taylor series, the better the approximation or the method. Here it takes us all the way down to a coefficient of h to the fifth. So we have a fourth derivative of f here, and we have this funny constant. Of course, this constant comes from what we're calling n and what we're letting n represent. Normally for Simpson's rule, at least often people like to double the number of subintervals from what we're using for the midpoint rule and the trapezoid rule. And when we do that, then actually this constant becomes 180. Okay, but if we want to keep n just the same as midpoint and trapezoid, so we could just think of a weighting, then we would use 2880. Okay, so Simpson's rule is simply just a weighting of the two other rules, and so it's easy to get this Taylor series if we just think of the weighting that way. So we take 1/3 of the 1/3 of the trapezoid rule. That's what this is. Plus, and that we get that Taylor series plus 2/3 of the midpoint rule series, and subtract that off. We end up getting a nice series for this error, and we look at the lowest non-zero term here, and that's it. And using the same modification of that term, and we end up getting our nice bound, which is right here. Well, right here. This down here, this shows just how you can modify it if you wanted to use 2n instead of n. Okay, so then right down here, I have some more code, which has to do with just examples of using these rules now. Let's actually just do them on an example. So here, let's let g of x be that, and n equals 10 subintervals, and h, so you're taking from 0 to 4. Let's just take that and divide it into n pieces. Here, this actually computes the trapezoid rule right here. So a is like the beginning of each subinterval, and each subinterval is length h, and you're just kind of, this is what we're doing every time right here, just finding the average of two heights and then multiplying that by width. For the midpoint sum, just taking h times the function evaluated in the middle of the subinterval, and you're adding that up. Simpson's rule, we're just weighting it, so that's kind of nice code for just writing that out. And in general, then we have the actual, we'll just compute the integral here, and then we can compare these things. So when we execute, we'll see the results. So the trapezoid rule, the midpoint rule, Simpson's rule, actual rule. Look how close Simpson's is to the actual. Very good approximation. In fact, right here, the error bound. So this is the actual error right here. How far apart they are compared to what we'd get if we were using a bound for the bound formula for Simpson's rule, which was right up here. Using that bound formula, that's where we get that quantity right there. Okay, so you can kind of see what we're doing. So here's where you're actually using the bound formula right here. What we did is we took the fourth derivative of g itself, and then we evaluated that fourth derivative at x equals 4 at that endpoint, because the fourth derivative is the largest at 4. By, if you actually look at the fourth derivative, let's see, the fourth. Well, actually, the fourth derivative is really just a constant, I guess, because it's 5. Let's see. Yeah. Let's see. No, it's let's see. Yeah, the fourth. Oh, it's not a constant. But it's a power. Let's see. Excuse me. So the first derivative you go down to 4. Second, you go down to 3. Third, you go down to 2, and the fourth you go down to 1. So it's a first degree. So it's just an increasing function, power function, just x to the first power. And so the largest that can be would be at that end. So that's why we're plugging in 4 here. And then this is b minus a, and then n raised to the fourth. And we had n in the computation. So we end up getting this fraction here. And notice, yes, this really is less than the error bound. So the error bound seems to be pretty accurate here. In fact, the error is like twice the actual even. Okay. So here's a little thought too. What if the fourth derivative is 0? Well, for Simpson's rule, realize that we're using a bound on the fourth derivative, right? Bound on m is representing a bound on the fourth derivative. So what if the fourth derivative is 0? That means we can choose m to be 0. Well, if m is 0, then the error is less than or equal to 0, which means it's equal to 0, which means it's exact. Amazing. Simpson's rule actually works. So we've gotten far enough into the Taylor series to ensure that anything with a fourth derivative of 0 will actually have an exact result for Simpson's rule, no matter how many n or subintervals we use. Doesn't matter how many we use. We can use 1 or 2, 3. So we don't have to. It doesn't really matter. We'll have an exact answer. So cubics. You take any cubic polynomial, the fourth derivative is 0. That would work. And let's see. Here's an example. Here's a cubic, and let's actually run the computation. So trapezoid, midpoint, Simpson's actual. Look, they're the same. It worked. And look, and notice what the n was. N was 2 in the computation. Okay. All right. Now that's kind of an exciting idea that Simpson's rule actually gives exact results even for cubic polynomials. Now, actually, if the second derivative is equal to 0, that'll actually ensure the trapezoid rule and the midpoint rule will give exact results. That happens for anything linear. So if you have something linear or straight line-ish, then the trapezoid and the midpoint rule should actually be exact. And you can run and see they all have the same thing. Yeah. And thanks for watching.